After seeing all these examples, let's now see the proof of Bourgain's theorem. And remember, Bourgain's theorem says that if we have some finite set V, in our application V will be the set of vertices of a graph, and we have a distance function over those vertices that satisfies the triangle inequality, and in our application D will be the optimal solution of the Layton-Rao relaxation, then it's possible to find a distribution over subsets of V such that if we call FAV the distance of V from the closest element of A, then for every pair of elements U and V, the expectation for a random set A sampled from the distribution D of FAU minus FAV is at least the distance between U and V times some error factor, which is at least 1 over log V. And we will prove this theorem for the same distribution that we came up with after considering all those examples. This is the distribution where first we pick a random density T uniformly at random between powers of 2 smaller than n, where n is the size of V. And then independently, we're going to pick every element of V to be in the set A with probability 1 over T. So after T is selected, the set A will have, on average, size n over T. Now here is a key definition in the proof of this theorem. Let's fix a pair UV, and we're going to prove that the expectation of FAU minus FAV is at least 1 over log n times the distance between U and V. And let's define RV sub T to be the distance from V of the tth closest element to V. So we look at V, and then we sort other vertices according to how close they are to V. Then we look at the element that in this sorted order comes up in position T. Then the distance from V to this vertex is what we define to be RV sub T. However, we are going to cap this distance to the distance from U to V divided by 3. Here this constant 3 is not very important, could be just any constant bigger than 2. And we give the same definition for U. So RU1 will be 0, RU2 will be the distance from U to the second closest element to U, and so on. Then we're going to call T star to be such that when we look at the T star closest element to V, this is still less than the distance from U to V divided by 3. And when we look at the T star closest elements to U, those are still a distance less than duv divided by 3. But then when we look at the next power of 2, so we consider 2 T star elements, then at least for one of V and U, we end up seeing elements whose distance from V is bigger than duv over 3. Maybe we see that for both of them, but if we see it for at least one of them, then that's the definition of T star. Now, given those definitions, here will be the key lemma in the proof. That for every parameter T less than T star, although we will only use this for parameters T that are powers of 2, when we condition this expectation to the choice of a random A for that particular parameter T, so the choice of a random A where every element belongs to A with probability 1 over T, then this conditional expectation is going to be at least up to a constant, the sum of the distance from V to the 2 times T closest element, plus the distance from U to the element which is in order 2t of increasing distances from u, minus RVT minus RUT. The reason why this lemma is essentially all of the proof of Bourgain's theorem is that from this to Bourgain's theorem is just a one-line calculation, because in order to compute the actual expectation, we can then take the sum over all t that are powers of 2 of this conditional expectation times the probability that that particular value of t is selected. Then we can bound each of those conditional expectations by this. But when we do that, this becomes what's called the telescoping sum. So it's a sum of terms where every next term cancels the previous term. And in fact, all those RUT, RVT cancel out, except when t equal 1 and when t is equal to 2t star. And so we are left with this lower bound. But then RV1 and RU1 are 0. And at least one of RV2t star and RU2t star is the distance from u to v divided by 3. And so the whole thing is at least some constant times the distance from u to v divided by log n. And so this is Bourgain's theorem, that this expected L1 distance between u and v in this embedding is at least the actual distance divided by log n. So it remains to prove this key lemma. So let's try to understand this conditional distribution. So we have u and we have v, which are a distance duv. So when we look at the 2t elements that are closest to u, at least one of them will have to be a distance RU2t or bigger. So if I consider the number of elements whose distance from u is strictly smaller than RU2t, the number of such elements is at most 2t. Now let's look at v and consider the t closest elements to v. Now all of them have distance at most RVT from v. So if I look at the number of elements whose distance from v is smaller than RVT, well, the number of such elements is at least t. Now we pick A so that for every element A of v, the probability of putting it into the set is 1 over t, and the probability of not putting it into the set is going to be 1 minus 1 over t, and those choices are made independently. So this means that there is a constant probability that A is going to completely avoid the set of all elements that are a distance less than RU2t from u. Because there are 2t such elements, each of them is picked with probability t. So on average there's going to be 2 elements or fewer. The way this is distributed is pretty close to a Poisson distribution. So there will be a constant probability that we actually pick none of those elements. But what happens if we pick none of those elements? Well, it means that the distance from u to the closest element of A is going to be bigger than RU to t. But also with constant probability and independently because both RU to t and RVT are less than the distance from u to v divided by 3. And so those are disjoint set. So also with constant probability and independently, A picks at least one of those t elements that are close to v. And so we can also say that with constant probability, FAV is going to be smaller than RVT. Now when those events happen, which is with constant probability, this difference is going to be at least RU2t minus RVT. So the contribution to the expectation of the case in which these events happen is at least some constant times RU2t minus RVT. Now let's do the same reasoning, but with the roles of V and U interchanged. So let's look at what are the 2t elements that are closest to V, and let's look at what are the t elements that are closest to U. Now we can do the same counting argument as before, and we can say that there is a constant probability that the set A is going to avoid all the 2t elements close to V, and it's going to pick some of the t elements closest to U. Notice that when this happens, the event that we described before does not happen. So those are two disjoint events. And that means that their contributions to the expectation can be added up without double counting anything. So when with constant probability we are avoiding all the 2t elements closest to V, and we are hitting some of the t element closest to U, then FAU is going to be smaller than RUT, and FAV is going to be bigger than RV2T. So that when this event happens, this difference is at least RV2T minus RUT. Now we can add up those two contributions to the expectation, and this is what we're going to get. Now, wrapping up the argument by what we call the telescopic sum observation, we're going to get that this expectation without conditioning over t is going to be at least 1 over log n times the distance from U to V. And then in turn, this implies that we have an L1 mapping where the L1 distance between points is at most duv and at least 1 over log n times duv. All the steps were constructive, so that also means that we're able to constructively round the Leighton-Rowe relaxation by only losing a factor of log n.